Hello, everyone. My name is John. We are super excited to be here at LINE Developer Day because it is actually our first time. I think we are here today to talk about implementing observability practice on Kubernetes. So to start with, I want to give a short self-introduction. My name is John. I am a site reliability engineer at LINE Taiwan, and currently I work at SRE Team. I'm primarily responsible for providing observability solutions that allow application teams to actively debug in distributed systems. And I'm interested in Linux networking, distributed systems, and open source projects.
My name is Wei, a site reliability engineer at LINE Taiwan SRE Team. I usually focus on setting up and maintaining the Temple platform, as well as organizing some examples and articles on integrating OpenTelemetry into the user's application. In addition, I also cooperate with my teammate to maintain the traffic ingress controller, which is deployed to the user cluster, and provide technical consulting. I'm a golfer and I'm interested in Kubernetes and serverless technology. Sometimes I will contribute some open source projects like Web Framework, Gene, and Grafana Temple, etc.
So for today's section outline, we want to start with the background and traditional monitoring practices at LINE Taiwan. And then I want to show an overview of observability platform which we built. Next, I want to talk about adoption status and current practices at LINE Taiwan when we introduce observability platform. Next, I will share our experience about challenge of adopting from application team. Last, we will share some use cases from application team for using it to do troubleshooting. Okay, let's begin with traditional monitoring practices and a little background introduction. Last year, in LINE Developer Day 2020, we introduced Kubernetes adoption status at LINE Taiwan. For previously Kubernetes adoption status, we mentioned that we had managed over 20 projects, 50 clusters, and more than 130 application configs for all application teams in Taiwan. Well, this year by October, the adoption status of Kubernetes in LINE Taiwan has increased. We have almost 40 projects, 70 Kubernetes clusters, and over 650 application configs. The number of project counts from 20 to 40 is double that of last year. For Kubernetes cluster, from 50 to 70 has increased 40% compared to last year. And for the application configs, which are Argo CD applications, from 130 to 650. So it's almost 5 times less of last year. You might be wondering how we provision a great number of clusters and how we manage and operate multiple clusters. Thanks to our team partner, Verda team, who provides one of in-house solution, Verda Kubernetes Services, also known VKS, which is a private Kubernetes service for serving LINE applications. So Verda is a private cloud service for LINE. And we also have Elasticsearch services called VES and object storage services called VOS, etc. So these infra services are provision resource for cloud computing and cloud storages. As SRE team, after provisioning clusters, we have been committed to provide operation, management, and monitoring services for all application teams in Taiwan. So before we get into detail of monitoring practices, there is a saying that I have learned and I want to share to you. Running a product without any monitoring is like not running the product at all. So which is mean monitoring plays an important role in production. Okay, let's talk about traditional monitoring practices on VKS. The practices might not flexible enough to use before we get involved? Well, there were various traditional approaches for application teams to monitor applications, and I will cover some common approaches. So imagine that application team wants to run application or services for customers. They will apply for a Kubernetes cluster to deploy applications. After they create a new cluster for running services, there are few monitoring components will be installed by default. So we have found there were three major pain points. The first one is the built-in log sender and Prometheus were both installed. However, this is not enough for daily application monitor. So let me elaborate more. The first one is logs. For collecting container logs, the built-in log sender actually it is a FluentD and it will send log to predefined Elasticsearch, which is VES. But the configuration might not be changed for customizing. The second one is metrics. For built-in Prometheus collecting metrics, it will scrap matrices, which is exported by exporter. However, it is all related to system level metrics like kube scheduler metric, kube API server metrics, kubelet metrics. The third one is tracing. So for distributed request tracing, we had a few teams use Lipkins for gathering span data or troubleshooting latency problem between microservices. However, it is rarely to see fully instrumentation for all components. So next, back to the second pain point, self-hosting Grafana and self-hosting Prometheus. As you may know, for self-hosting monitoring system might bring operation costs for application teams. For example, a Prometheus long-term storage problem like you want to show application metrics for past 6 months. And self-hosting Grafana is redundant deployment work for application teams. Grafana dashboard might deploy across teams, and for Taiwan services, it should be a single Grafana dashboard for serving for all teams. So lastly, for the spatial use case we found, application team would have self-hosting ELK stack for monitoring applications on Kubernetes. So the cost of self-hosting ELK may be expensive when application usage grow. And yes, there may need an expert in ELK stack to manage the performance and indices. So it's all about traditional monitoring approaches we found in application team for the past. So next, we will introduce an overview of observability platform we built.
The goal of observability platform is finding the root cause of the problem from data observation and provide better debug experience. The following are the two main goals. First, everyone using same tools and dashboard. We provide shared Grafana instance with multiple organizations for all projects. And we prepare data source and built-in dashboard for each project. In addition, if there are another data source, such as Elasticsearch or Ingress DB in a project, user can also use the Grafana managed by us to link and access data or create dashboard with alerts. Second, pooling of system knowledge for organization. Each project can using same dashboard and find out the details of incident from the same data source that can reduce the commutation cost. The experience of import telemetry data from application will be similar and can be shared. Different from the traditional monitoring methods mentioned earlier. For example, users need to open Kibana UI for querying log data in Elasticsearch. And users also needs open another Grafana for query metric or open zipping UI for query tracing data. In the observability platform, Users can see all data in one place by the dashboard in the same layout. In the following use case sharing, we will see the powerful ability in using three kinds of data to query and locate problems together. In addition, users need to integrate SDK when integrating metric and trace. For example, Open Census or Prometheus client for metric and Open Tracing, Elastic APN or OpenTelemetry for trace. By providing a consistent platform, users will have the same experience in integrating these SDKs, which greatly reduce duplication of work between teams. Observability platform provide the multi-tenancy support. We collect telemetry data from multiple clusters belonging to different projects. For example, the project A may have multiple environments like data, staging, and production. And telemetry data from different clusters will group by project, and the data in each project is isolated. As shown in the figure, each user will be given permission to access different projects according to the email group. When users access Grafana UI, they can only see the data of the project they belong to. Let's see the architecture overview.
Okay, let's get started with the log platform. So we use Grafana Loki as a log aggregation system. So all containers logs will be sent to Loki by a daemon called Prometheus, which is a collector to tell container logs and send to Loki. The only agent we install on user clusters is a Prometheus daemon set. So Prometheus is a log collector we can customize for teams to block sensitive string like personal information due to security policies. So in the diagram, you can see there are two different project teams use different clusters, including project A and project B with VKS clusters. So log isolate is matter for them, for team to query their own application logs. In order to implement multi-tenancies, we assign each team a tenant code, which is an identity for querying and storing log. Also, Prometheus will be assigned a unique tenant code to send to Loki. For users who want to query log in certain team, they may have to set up a tenant code in Grafana data source. So based on this architecture, you can see we only use a single data source, which is Loki, and we use it to perform log query. For the storage backend, so we leverage Verda object storages to perform a low-cost data storage and almost unlimited size and object counts. So next, for the metrics platform part, in order to perform high availability permission setup with long-term storage capability of metrics, we use Thanos, which is an open source project. It can help us to upload the time series metrics data to an object storage. Also, Thanos can help keep long-term metrics data in object storages and using downsampling feature to improve metric query performance. For the multi-tenancy usage, we separate the bucket of object storages by each project team. Each project team has their own Thanos querier for querying metrics data from different organizations in the same Grafana dashboard. Most important of all, as the role of SRE team, we do have a global view of all cluster metrics, since we need to know services availability of all applications. So we set up a global Thanos querier for querying metrics across all user clusters. So this component is not showing on the diagram due to the simplicity of drawing.
Next, we will introduce the architecture of tracing backend. We choose the Grafana template for our storage backend and using OpenTelemetry collector for trace data preprocessing. In the figure, we can see that trace data of the application will be sent to the OpenTelemetry collector in each project, clustered through the sidecar deployed in the application part. And trace data will be preprocessed in OpenTelemetry collector and sent to Kafka topic by projects. In the observability platform cluster, we also deploy OpenTelemetry collector for consuming the trace data from Kafka topic and sent to Grafana template with the tenant ID for multi-tenancy. Then trace data will be stored in Verda object storage, which is a S3 compatible object storage. For the users of observability platform, they can access the trace data from Grafana UI, and Grafana will query the trace data from Verda object storage by Grafana template. Okay, let's see the statistic of object storage usage in Loki, Thanos, and Temple. For logs, 30 terabyte of data and a total about 20 million object count in 1 month retention. For metric, 60 terabyte of data and a total about 360,000 object count. For trace, 20 terabyte of data and total about 1 million object count in 1 month retention. And both Loki and Temple have a component called compactor. This component will do the retention works and compress the old block in the object storage for preventing data size and count growth unlimited. The next part is manage Ingress controller. First, we choose traffic as a Kubernetes Ingress provider. Second, traffic will be deployed to Kubernetes cluster for each project. Third, the traffic is a part of observability platform with integrated sidecar for trace and export metric. Let's see the architecture of managed Ingress controller. We deploy traffic as a daemon set in Kubernetes cluster of each project with the Jaeger sidecar. Traffic Ingress controller will watch the event of Kubernetes Ingress resource and a custom resource like Ingress route or middleware for automatic generate routing rule inner traffic. When the incoming network traffic from Verda load balancer, the trace data for each request will send to the OpenTelemetry collector and go through the data pipeline of our observability platform. And why we choose providing managed Ingress traffic controller? Because all requests incoming cluster will go through the Ingress component. By providing a unified solution, we can collect as much data as possible to our system. With this information, we can provide common dashboard and help each cluster monitor the Ingress controller. The next part is adoption status and current practice.
So next, I want to share about observability platform adoption status of teams at LINE Taiwan. There are several project teams adopt, including LINE Today, LINE Shopping, LINE Music, LINE Hub, LINE Travel, LINE Spot, OA Plus, and stickers. So let's take a look at the statistic of user counts on Grafana we hosted. So overall, we have created 34 Grafana organizations 200 users and more than 120 activity users in the last 30 days. Also, we help to maintain more than 750 dashboards and manage 200 data sources and 300 alerts across all Grafana organizations. Organizations collect data from a variety of sources, including Prometheus, Loki, Tempo, InfluxDB, Elasticsearch, MySQL, or more. Most of team in LINE Taiwan using Prometheus, Loki, and Tempo for doing observability that help to debug in distributed system. Grafana support many different storage backend for data source, like InfluxDB, Elasticsearch, or even MySQL. That can be used. We keep flexible for users who want to use different storage backend. Next, I want to share some statistic data of 3 major telemetric data that observability platform can perform. So for ingesting log, we have 300 million logs line per hour and over 40 billion a week. For monitoring metrics series, we have 16 million metrics. For distributed tracing spend, we have 200 million per hour and over 20 billion a week. By default, we keep logs and traces data for 1 month retention, and this is only for debugging usages. Next, you would probably want to know how to manage agents for more than 70 clusters. Yes, it is a tough work when we operate for upgrading, deploying with so many components installed in clusters. I want to talk about how we manage multiple applications across many clusters within a monorepo. In order to deploy multiple Argo CD applications from a single monorepo, we have used Argo CD application set control to deploy applications on multiple clusters at the same time. All these features are controlled by only a single instance of an application set customer resource. For instance, you can see the example YAML in the right-hand side. When you want to deploy an event exporter to all 70 user clusters, we will have to the cluster generator to generate parameters which are requested into the value of name and servers. So the following telemetry data are key to achieving observability in distributed system. The first one is logs. So log is a record for events that happen within an application. They are easy to generate and instruct. And most application frameworks, libraries, languages comes with supporting for logging. So the second one is metrics. Metrics is a numerical representation of data. It determines a service's or components' overall behavior over time. So we gather metrics on response time, system uptime, and number of RPS. Typically, we use metrics to trigger alerts whenever a system value goes above a specific threshold. So next one is trace. A trace contains end-to-end data about the service code chain in the context of request and transaction. Tracing is better suitable for debugging and monitoring complex applications because it provides context of other components of observability. So with these 3 telemetries help us to better understand the performance and behavior of distributed systems. Next, I will share our experience about challenge of adopting from application teams.
When we adopting observability platform for application team, we face some challenges. The one is new query language need to be learned, like LogQL and PromQL. And the other one is instrumentation of metric and trace. It means engineer needs change its code for expose metric and integrate trace SDK. And how to deal with the changes. First, we prepare the internal hands-on workshop for teams. Due to COVID-19, we held an online workshop at Zoom. As in the photo below, each SRE member gave an introduction on several topics, from principle to example, for users who use our platform. It mainly contains the following content: Loki and Prometheus storage principle, LogQL and ProQL sentence introduction and example, how to integrate metric and tracing into application, and which functions are included in the built-in default dashboard and basic operation of Grafana. Second, we prepare the default dashboard for each project, including the uptime, Kubernetes deployment, job, event, and traffic query per second or latency. All dashboards are pre-configured in each Grafana organization, and users can be accessed directly out of box. We hope that even if user is not familiar with the design Grafana dashboard or integrate metric of application, they still has a common dashboard to check problem. Additionally, the managed Ingress controller also has some out-of-box feature. For example, built-in TLS certificate and traffic common middleware like redirect to HTTPS, gzip complex, etc. We also integrate structured load, tracing agent, and export metric, and user only need apply YAML like the picture that can using all feature. And then we will start for use case sharing.
Okay, so we will share some use cases for using observability platform. And first, I want to share a use case from application team, which is LINE Spot. So we collect some use cases from application team. For the first case, we have 4 steps to easily locate the problem, from getting alerts, checking metrics, inspecting log, and using LogQL to calculate the average elapsed time to check processing time pattern. One problem that they faced here was front-end pod restart randomly. The reason of restarting is liveness check fail. As you can see, the container restart alert message sending to Slack. For handling notification, we use Grafana alerts to managing alerts. Actually, this is an embedded alert manager. You can configure its context point, notification policies, silences, and template from the Grafana alerting user interface. Next, let's move to check metrics of container CPU and memory usages. There are 2 peaks when server restart up, but it seems to be normal when the server is loading up. So in this situation, we can see there is no abnormal status, but we still could quickly switch to another panels to know server status. For inspecting log here is the Grafana log panel in order to locate and shorten the incident period. In Grafana log panel, user could use LogQL to filter some keywords they are interested in. For searching server restart message, we could use the filter like server is listening on port 3000. When they found server restarting message, server was restarted around 2 p.m. For now, from metrics to log, we could have visibility into system in the same dashboard. Next, there is a feature called matrix queries, which can extend log queries to calculate values based on query result. After checking the last request before restart, they used matrix queries to extract log, and they found there was an elapsed time peak in the specific pod. Any pod, they found the peak of elapsed time always comes with a specific query string and easy to reproduce in the other environment. So it turned out that there was a regular expression mistakes in the query string.
For use case 2, we will demo how to interactive observation with metric, log, and trace. For the beginning, we find out 500 HTTP error from dashboard. Then we found the relevant log and locate the error log for request. Finally, we open the trace view and jump to logs in span of trace. Let's start for digging. We can see on side is the traffic Ingress controller dashboard, which we provide to each project. User can observe the number of query per second, latency, upstream server, and errors from this dashboard. First, we can find the error rate of HTTP request has increased during the time interval in the red circle from the dashboard. For common case, when developer facing errors, they usually want to find log. So we can click the Explore button and open the split view. In the split view, we can click the button of red square, and a time range of 2 views will be synced. And we can find Grafana auto make log query by the label from the metric in the left view. Thus, we can synchronize the time range of log query by dragging the time interval on the left view. Through the above operations, I can narrow the time range of the time query access log. And next step, we want to locate the error log. The traffic has pre-configured structured access logs in JSON format. As shown in the figure, we can filter out logs with HTTP status code through the logql query statement. For example, we filter log by request, host, and origin status. After locate the error log, we can open the detail of it. And we can find some information of access log, like HTTP method, path, code, etc. Additionally, the trace ID field will auto-detect and generate a tempo button in the red box. Then, we want to see the code state of this access log. Click the tempo button and the trace view will open in the right-hand side. In the trace view, we can see the code stack from traffic to our application. As you can see on the picture, we see that green bar represents the traffic process, the request, and yellow bar represents our application process request. The metadata in span of trace also can be seen in this view. For example, we can see the metadata error is true in our application. So we can guess the error happened in our application. Then we want to check the stack trace in the log of our application. The logs of this span button in red box can be clicked. And the log of the application part in this span will show in the right view. In the state trace of log, we can see some panic appear in logs. Okay, it is very good. It seems that we have found the root cause. The above is a complete process of finding problems through the 3 telemetry data of measuring log and trace.
Okay, so that's the end of use cases. Next, I want to share some roadmap and next step we will plan to do. So we have provide observability services for teams, including metrics, logs, and traces, and this telemetry data are crucial for finding problems. We believe that the combination of different observability signals become a must-to-have feature. So we are keep working for the next steps. Like the first one, metrics to trace, an example of traces and correlating to metrics unlock the ability to click through a matrix. The second one is trace to matrix. Trace can be minded to derive context-rich metrics that can help us identify and isolate the problem. So last one is application monitoring and error tracking. So we would like to integrate Sentry and Web Vitals. Lastly, to summarize here is today's key takeaways. So first, traditional monitoring practices are not enough for team debugging in a distributed system. The second one, observability platform brings a consolidated dashboards and pooling of system knowledge across organization. Third, current observability practices speed up for team to achieve actionable insight from data. And last, we share adoption challenge experience and use cases from application teams. So that's the end of our sharing, and we hope you are enjoying it. That's it. Thank you for listening.
Thank you.